I will start by introducing myself. So my name's Nelson. I recently graduated from BYU with an undergraduate degree in economics this past April. And since then, I've been working as a data scientist at Branded Entertainment Network. And just a quick plug, she said to announce any jobs at Slack, but as long as I'm thinking about it, I'm not going to remember on Slack later. Next year, we're hiring like 4 new data scientists. So if you're interested, we're a pretty cool company. All right, so we're going to be talking today about unstructured data and how we can get value out of it. So I'm going to give you a quick overview of the things I'm going to talk about. First, I want to motivate the topic, just talk about why it's important and understand unstructured data a little bit. Then we're going to look at image data, then text data, then combining the two through feature extraction. After that, I have some code examples if I still have way too much time left, or you're interested in just seeing the actual code. And then there's time for questions at the end, but please feel free to interrupt me if you have a question during it. Some people like to wait to the end, that's fine too, but feel free to interrupt. So, unstructured data. First, let's talk about what structured data is. Structured data is what you see in an Excel sheet, right? You have columns, you have rows, and you have numbers. And it is beautiful, and every data scientist wants a nice spreadsheet that they can just plug into a model and spit out some nice predictions on the other side. Unstructured data is a lot more complicated. It includes any sort of text, video, image, audio, anything that you can't just stick in a spreadsheet and look at the numbers for. So there's a lot of it. I recently read a report that about 90% of the data created every day is unstructured. So that's a lot of the data. So most, from my experience, and I would wager to bet for most companies, structured data is what makes up most of the data being used to make decisions, to help inform leaders, things of that nature. So unstructured data is a huge data source that has a lot of untapped potential. So I want to show you guys a quick look at what my company works with. So we do influencer marketing. Oh, it's right here. So we work with influencers and brands to help run marketing campaigns, basically. And we cannot understand why someone clicks on something or what people think about some sort of YouTube video just by looking at how many likes it got or how many views it got. Because there might be a video of a cute puppy that got hundreds of thousands of likes and a fail video that got hundreds of thousands of likes. And they're very, very different pieces of content. So we have to use the audio, the video, the thumbnail images, the comments from users to understand exactly what is going on so that we can make good decisions. So to use unstructured data, deep learning has been the key so far. Deep learning has not always been super strong with the tabular side of data, but with unstructured data, it has had some big wins. Things like object recognition, translation. Google Translate's just a big neural network helping you translate languages. So it has been the answer so far to using unstructured data and getting a lot of value out of it. However, it is not always easy to use. Anyone who has ever built some sort of image classifier has probably had an experience similar to this. where you thought your neural network was going to do one thing, and it did something insane. So deep learning is difficult for a lot of reasons. One of them is because deep learning works best when you have insane amounts of data. That's why companies like Google, like Amazon, like Apple are able to use deep learning and do it so well and see such good results from it. It's because they have insane amounts of data. Most companies do not have that much data and do not have the time to process that much data. Another reason, kind of similar, is because it takes a lot of compute time and power to build good neural networks. So when you have millions and millions of images that you're processing, if you're running that on the CPU on your computer, it's going to take you years. Whereas Google has hundreds of thousands of GPUs specially tailored to their processes to help it go faster. So a lot of people also don't have the compute power to just train giant neural networks to do what they want to. The last one is sometimes neural networks are just confusing. There's a lot of different types of neural networks. You can use convolutional neural networks. There's LSTMs. There's things like attention. A lot of really complicated math stuff that people have figured out, but you kind of need a PhD in math to understand it. So that kind of brings me to what this presentation was titled online. A lot of you probably saw that it said something like, you don't need a PhD to use unstructured data. So I'm guessing that everyone here either doesn't have a PhD and wanted to get better at unstructured data, or has a PhD and came to tell me they're smarter than me. If you are the second one and you have a PhD and you spent your life studying deep learning and neural networks, I appreciate you very much, because people like that are the reason that people like me, who have an undergraduate degree in economics, know how to use neural networks and to get value out of them. At Ben, we have a team of research scientists who spend their lives studying new ways to build neural networks to get a lot of information out of the type of data that we collect. And they're brilliant. And sometimes they try to explain to me what they're doing, and I have no idea. So people like that are incredible. But because of people like that, and because of companies like Google, Facebook, who open source their stuff, it's actually really easy now to be able to take what they've done and to use it to add value to your own company or your own projects that you're working on. So the goal of this presentation is that everyone will leave here understanding how to take what these companies have done, change it to make it your own, and to get a lot of value out of it with whatever type of data you're working with. So to do this, I decided to do a case study. Thanks to Kaggle and the internet, there was a beautiful data set from Goodreads that was available. And this data set is filled with a bunch of things like page numbers of books, things like that. But it also had the cover of the book, so the image, and then a description of the book, which you see here for Harry Potter and the Goblet of Fire. So I took these two things and I used them to see if we could predict what the genre of a book is. So we had 77 different genres. So it's a lot. Some of them are a little messy, but we have 77 genres, and we're going to see if we can take the unstructured data we have here and figure out what genre a book is just by using that. All right, so we are going to start with image data. So we talked a second ago about how giant companies have used giant data to build giant neural networks and have trained them for hours and hours and hours on end. So one of the greatest advances in computer vision, probably the one that propelled deep learning forward more than anything else, was the ImageNet dataset and transfer learning. So all these pictures you see here come from the ImageNet dataset. For those of you not familiar with it, it's basically an insane number of classes with about 1,000 pictures for each of them. Most neural networks that are trained on these are trained on 1,000 classes of 1,000 images each. And so there's things from animals to people to cars to flowers to whatever you can think. But what this did is people like Google built neural networks, trained them on all of these different images, saved the weights, and made those available to everyone. So we could take those weights that learned features about different pictures and use them in a different domain. So that was the first thing that we The first approach we take when trying to work with our book set. So one of these models that have been trained is called VGG11. It's one of the smaller models, and I chose it just because less compute time and it's pretty simple. So really quick to go over what this model is. So we have at the top the blue layers, then yellow, purple, green, red, and a darker blue. So so the picture goes into this neural network from the top, where it says size 224. You can see that kind of small. But all the way down through the red, it's going through convolutional layers, which we can think of as learning features. So it's learning things like, what do these colors mean? What are these lines on the side? Where are the edges? Things like that. And the last three layers there that say FC are the fully connected layers of the neural network. So they take the features that were learned from the convolutions and understand how they are related to the genre in this case, or whatever we're trying to predict. So the way Google did this is it took all of those images, passed them through, it learned features from those images, and then used those features to predict which class it belonged to. So was it human, was it a car, something like that. So we can take those weights and use them for our Goodreads data set. So I wrote out here the steps for transfer learning. So the way this works is first we load the model with the pre-trained weights that were trained on ImageNet. Then we take, so at the very bottom, there's the last FC 4096 layer. So what that means is that there's 4,096 features going in, and coming out, there's 1,000 features, or 1,000 classes, because it's trying to predict one of 1,000 classes. With our data set, we only have 77 genres, so we need to change that layer. So we replace that last layer with a new layer that takes 4096 in and only puts out 77 for our 77 classes. So once we do that, we have a model that's ready to be trained and make predictions. So we really like that Google learned all these features for us from all these other images. So we want to make sure all of the convolutional layers stay the same, because they have learned from a lot of pictures and a lot of data that we don't have. I think our data set was 10,000 images. So they trained it on much, much more than we have. So what we can do is we can freeze the gradients of all the convolutional layers. All this means is that we are going to stop tracking the gradients so that it's not updating weights. So the weights that are there stay the same the whole time. It's not learning any new features in that part of the model. And then with the last three layers that are fully connected, we want to keep the gradient there, because we are not trying to learn how those features translate to cars and people and flowers. We want to learn how they translate to genres. So we can keep those with the gradient so that they're updating the weights and learning those new relationships. So from this point, we can just train the model on our data, and that's what I did. So I compared this transfer learning model to another model that was exactly the same architecture. So I took the VGG11 and did not have any pre-trained weights. And there's a pretty big difference. So on the right, you can see the numbers. Without transfer learning, we got an accuracy of about 27%. And with it, we increased it by almost 7% to 34%. So on the graph.
Is that the loss curve on the graph?
Yes. So on the graph, we have our losses. It's too small to read what they are probably. The red line is without transfer learning, the validation loss. So you can see it goes down for a little bit till about the 20th iteration, and then it goes up. So we took the best loss and used that model to make predictions. The green line is the training loss for the model without transfer learning. So it got better and better and better, but it started overfitting. And then we have the yellow line, which is the validation loss for the model that we use with transfer learning. So a few things to point out here. First of all, it started better than our other model ever got before it even trained. So for one, that's pretty impressive. Secondly, you notice that it got to its minimum probably like in half the time that our other model got to its minimum, and the minimum was way lower. So we cut our training time in half, and we have a model that performed way better. So those are two things that transfer learning does a lot for us. So This is something that has been researched a lot. If you've worked with image classification, you've probably used or heard of transfer learning at least. So the question now is, how can we take transfer learning and make it so much more custom to our needs? So we're going to talk about fine-tuning. When we talk about fine-tuning a neural network, there's a lot of things that can mean. I said fine-tuning for lack of a better definition or term. It can mean tuning the parameters, the learning rate, the optimizer, a lot of different things. We're going to talk about it with respect to fine-tuning into our data set, so whatever our domain is. So let's go back a second and look at this. So these are the images that our neural network, our pre-trained weights were trained on. There's a lot of images here, but they don't look like this, right? None of them look like a book cover. So the pre-trained weights that we are using learn features from these other images. And there's a lot of images here, which is why transfer learning works. But you can think of it kind of like, what if you had to describe to someone what a zebra looked like only using the features of a butterfly? Like, maybe there's some similarities with the legs, a little bit of fur, but it'd be difficult. That's not maybe a fair comparison because they use so many different classes to train these giant networks, but it's something along those lines. So what if we can learn features from our data set while still keeping the power of the giant data set? So one way we can do this is by fine-tuning it to our data. So we can do this by replacing our last layer like we did before with the regular transfer learning, and then freezing the gradient of all of our feature layers. So they're learning, we're not going to learn any features, and we're just going to have our fully connected layers learning how those features relate to genre. We can run that through one iteration of training, and after that first iteration of training, we can unfreeze the next highest layer. So the bottom red layer, we can unfreeze and start tracking the gradient. We can train it one more iteration. Same thing again, unfreeze the second to last layer, train it again, and keep going until we've made it all the way to the top. So what this does is it keeps most of the transfer weights that we have, and it slowly introduces the features from our book data set into our model. So a few tips just for doing this. Normally you're going to want to use a lower learning rate. You'll see why in a second when we look at the loss curves for this kind of thing. I kept all the learning rates the same when comparing models to try to make it a fair comparison. Same learning rates, same optimizers, same test sets. So along those same lines, learning rate annealing, so slowly decreasing your learning rate as your model trains is extremely helpful, because when we are fine-tuning our model on our data set, we are slowly starting to overfit more and more because it's learning exact features of our training data. So a few other things to think about. When we're fine-tuning it to our data, that's going to have interactions also with other types of tuning we're doing. So things like the optimizer, learning rate, augmented data. We have to think about those things too. Also, it's not a hard and fast rule that you train at one epoch and then unfreeze and then do another and unfreeze and do another unfreeze. You could do 2 or 3 and unfreeze. It's something that you can play around with and see how it works. Another thing is how many layers you unfreeze in total. So if we look at our model again, the very top is learning a lot of high-level features about images, whereas our layers closer to the bottom, the red ones, are learning like the fine details of images. So it may be that you don't necessarily need to retrain and unfreeze from all the way from the top to the bottom. You might only want to unfreeze the red layers or the green layers. But that's something also to consider when fine-tuning to specific data sets. And then lastly, just my little disclaimer, this doesn't always work. The more data you have, the better it's going to work. Certain data sets maybe are just similar enough to ImageNet that it's not going to help that much. But all that being said, when we compare it to before, we see a better accuracy when trying to predict the genre of books from their covers. So if we look at the accuracy, we improved by about 0.6%, which not a huge increase, but the training time, if you look at the loss curve, we hit our minimum a few epochs sooner. So we took even less training time, and we got a slightly better model. So that's a win-win. You can also see with our brown line, that is the fine-tuned validation loss. After it hits its minimum, it shoots off into nowhere pretty quickly because it's overfitting a lot, which is why I mentioned thinking about the learning rate and decreasing the learning rate. So those are a few things to consider. But we see here that fine-tuning it to our image data set improved our model. All right. Are there any questions about our image models and fine-tuning? Great. We're going to move on to text data then. So when thinking about text data, so the last model that we built, I used pytorch because it's really nice and handy. For language models, there's a few different libraries that have been built on top of pytorch that are extremely useful. One of them is called Flare, which I like a lot. So if you are familiar with language models at all, lately there's been a lot of state-of-the-art models coming out. On this list here, if you can read that, it says there's BERT, there's Elmo, there's fast text, there's the GPT-2. A lot of the state-of-the-art language models that have been built are included in this library. So with language models, similar to image models, transfer learning is a big thing. So instead of having some sort of ImageNet data set, researchers have basically scraped all of Wikipedia and trained language models on that. And the way language models work is they're given a chunk of text and they're trying to predict what comes next. And they found that that helps models understand a lot of the context of what's going on and the meaning of sentences. So this is what we're working with. So in the same way we use image models to fine-tune, we're going to fine-tune a text model on our data set. So Flare makes it really easy to do this. All you have to do is create your own corpus of data, which is basically just push all of your text data together. So we just have one big document of book descriptions. We load the model, and then we just say train. And Flare is set up in a way that it will train fine-tune the loaded model using early stopping, a learning rate that decreases over time. It takes care of everything. It's really, really beautiful. So we train that for a little while, and then we can use the model to extract word embeddings. So word embeddings are vector representations of words. So they help capture the meaning of words. For example, we might have a vector for the word king. That's this list of numbers. That means that's what king means. And then we might have one for like woman, which is another one. The cool thing about word embeddings is if we add those two vectors together, it will look just like the word embedding for queen would, because we're doing king plus woman. So it works in a really similar way to that. So it helps us understand the context of words. So these word embeddings are what we are going to use as our features for our model. Before we look at the results of the language models, a few quick tips for fine-tuning. Even more so than with images, data is huge here. If you only have like 100 sentences to train or to fine-tune a language model on, it's probably not going to do very much. So more data is always better. Another thing, so I pointed out there's a lot of state-of-the-art models incorporated in the Flare library. We have found at Ben that state-of-the-art is not always state-of-the-art. A lot of times, using something like BERT takes a really, really long time to run because it's this gigantic neural network and you're running it through hundreds of layers. And it doesn't actually add anything to a model. So one thing that I would recommend doing when working with language models is starting with the most efficient, quickest model you can find, see how it works, and then slowly work your way up from there. Don't just jump into the deep end and try to use BERT because it's cool to use BERT. Efficiency is very important when when using language models. So one last note is that I did this with Flare. There's a lot of library. Oh yeah, sorry.
I was just curious, how do you know?
Know what?
That you're not, the direction to go, I guess, or what to use, and not go.
As far as complexity.
Yeah, like if you're just starting out without that experience,
yeah.
How do you know that?
So you'll see in a second, we're going to put this into a model to try to predict genre. But generally what we do is we start with the lowest, most basic you can find. Like I used Flare here. There's also, oh, why am I spacing on it now? There's other libraries that do even like more simple stuff than Flare does. We usually use something like that to extract word embeddings and feed it into a model and see how it improves the metrics of the model. If it works really, really well, and we're like, we don't really need that much more out of this, we just use it because it's the fastest. If we say it kind of worked, but we want to gain a lot more out of this, we slowly start moving up. There's not an exact science to it. You kind of have to weigh how much benefit you're getting from it versus the time it takes to run. Because the difference between running, so I ran, Flare comes with its own embeddings. Running that compared to running BERT, probably like a 10 times time difference, which is pretty big when you're running it on 1 million paragraphs, right? So generally you start from the bottom, see how it impacts the model, and slowly work your way up until you find the sweet spot. I don't know if you've heard of the elbow method, but when doing unsupervised learning and trying to find the correct number of clusters to use when clustering groups together, you can plot the clusters on a graph, and it looks something like a curve. And there's usually a point at the curve where there's an elbow. It's a really steep, where you're not gaining very much more from it at that point, but the time's increasing. So something like that can help you figure out what the right complexity is for a model. Hopefully that helps.
Yeah, and then I'm assuming just through experiences where you know to go next.
Yeah, it's still kind of a guessing game.
Okay.
Like, I was actually reading a paper, and they were talking about training neural networks and picking hyperparameters, but I think it applies to most things with neural networks. They said that picking the right hyperparameters is something like black magic. You just have to get lucky or like, understand neural networks on a super deep level. So it's kind of like that. You guess, you experiment, and you figure out what makes the most sense for your situation. Yeah. Was there any other questions about this?
Justin, a good place to start, just to get experience, would be go through the fast AI tutorials, especially for NLP. It's nlp.fast.ai, and they'll run through a lot of what he's saying, especially when it comes to picking your hyperparameters and just getting around how to get started. There's videos and there's also exercises included with it that are just really good for that kind of getting to feel around in it.
Awesome.
Yeah, sorry.
No, that's great. Actually, that brings up another good point. Fast AI makes it super easy to do things like train for one iteration, unfreeze a layer, train for one iteration, unfreeze a layer. And I don't know if they have tutorials on it, but they have documentation that makes it really easy.
I don't know how deep the tutorial goes into their library, but I know that they have very excellent tutorials with accompanying examples that you just get from their website.
They do. And I included that on here. So one thing Flare does is it's just training and training and training to fine tune. If you're interested in doing something like we did with the image thing, where you unfreeze a layer after every single epoch, you can do that with language models too. I just took this approach because I wanted to show something a little bit different. Everything we're looking at for both image and text is pretty much universal across training neural networks. But yeah, Fast AI is a great place to start. Other places like Hugging Face, I don't know if you've heard of that, but they have a great library. But yeah, there's lots of people who have made language models really easy to use. So we took the word embeddings that we got from our model and put them through a feed-forward neural network. So just the fully connected layers of neural network to try to predict the genre of a book. And so we did one, I took one where I just took the flare embeddings, pre-trained, loaded as is, and one where I fine-tuned it on our book description and did it again. So here there's a pretty significant difference, once again, about 2% increase. So neither of these performed as well as the book covers did, but they still did a decent job as far as predicting my messy data. So here, once again, tuning our language model to our specific data set and domain helped improve what we were working on. Because, once again, what they scraped off of Wikipedia probably isn't all super similar to our book descriptions. Like, I'm sure some of that's in there, but a little bit different. So, moving on. So, we've looked at both image data and text data. A lot of times, especially in my work, there is tabular data, images associated with each row of tabular data, and text associated with each row of tabular data. So finding ways to combine them into a model that is going to provide more value with all that data together than any one of them separate is super important, and a good way to get a lot of value out of your unstructured data. So feature extraction. First of all, exactly what, oh, I think I broke something.
No, you're good.
Can I load again?
This is why I'm stuck here. Did my power turn on? Your screen went off. Let's end your show and try and there we go. Just go back to where you were. I will reset this.
All right, well, while she's trying to figure that out, we'll talk about what exactly feature extraction is. So when we looked at our image network, there was all of the feature layers before we got to the fully connected layers that helped us predict the genre. So we can take all of the features that were learned from those convolutional layers and spit them out as a string of numbers.
We're still good. They haven't broken anything yet.
So once we spit out a string of numbers, then it looks a little more like structured data.
There we go.
Okay, here we go. So it looks a little more like structured data once we put it through all those convolutional layers and spit it out as a string of numbers. So at the bottom, we have our fully connected layers, where they're taking 4096, a dimensional matrix as its input, and spitting it out. So if we want to get the features from this model, we can chop off the very last one that we added, so where we changed it from 1000 output to 77 output to predict the genres. If we just chop that off and take the 4096 features that it's passing to that one, we can take that as our feature vector and use it as features in our tabular data. So we can just take that as a row, 4096 features, and append it to our word embeddings. Because our word embeddings are just 2048 features, also a vector. So now we have whatever 2048 plus 4096 is, and we have something that looks like tabular data with a target, which is our genre. So once we chop off that last layer, you can just run your images through it like you're making a prediction, and it's going to spit out a vector that means absolutely nothing to you, but is what the machine learned as the features for that image. So we can take this and create a new model with it. So I just used a random forest, just out of scikit-learn, out of the box, and put the text data with our image data and ran it through random forest. And that improved on top of our best model by another like 2.3%. So by combining our image data, unstructured, and our text data, unstructured, into structured data and running it through a model, we were able to get a significantly better model than any of our other ones. So that is, in my line of work, that's like one of the biggest ways that we make the most out of unstructured data, is we just take the unstructured data, understand the features of it through the models, and then turn it into structured data to combine with other tabular data. Because, yeah, go ahead.
So what we mean is that before you apply the random forest to your last bottom fully connected layer, your previous model was applied with what, the softmax function before?
Yeah, yeah. So we were just taking whatever the highest probability was for the genre out of the last layer.
Okay.
Yeah. Yeah.
Is this top 1 accuracy or like top 5 accuracy?
So we just took straight, yeah, top 1. Yeah, the percentages are a little low, probably because the data was a little messy. I didn't spend a lot of time cleaning it up, because I just hoped Cackle did a good job.
What genres did you say? There
It
were
was 77.
That's substantially better than guessing.
Yeah.
Yeah.
So the highest percentage of one genre was like 15%. So this is a lot better than just guessing the highest genre. So in the end, by combining all the unstructured data, we came out with a better model. And this has a lot of applications in areas where you also have tabular data that has a lot of information, and unstructured data can supplement the information in your tabular data to create a really powerful model. So a little bit of code. I'm going to go through this fast because looking at code probably isn't that interesting, but I figured there'd probably be some people who are interested in seeing how to do these things. So this is PyTorch, transfer learning. So the first line of code, we're just loading the VGG11 model with pre-trained weights. The second line of code, we're taking the very last layer of our classifier, which is our fully connected layer, and replacing it with our new layer, which takes 4096 inputs and outputs the length of our classes, so 77. And then the very last 2 lines of code go through all of the parameters of our features, which is our convolutional layers, and freezes them, or turns off the gradient. So hopefully that makes sense. Also, with all this code, I have a link to my GitHub at the end that you can go and look at all of it. So it should be in a place where you can download it and run it yourselves if you want to. Second thing, when we're fine-tuning a model, so this is when we have our image model, we're fine-tuning it to our specific data set and unfreezing layers as we go. So this would go somewhere in your training loop for your model. So at the end of each training loop, we would want to sort through all of our features, which is the first line. So for each parameter, we are going to add a gradient to 2 layers at a time. And we do 2 layers because each layer has a parameter for the weight and the bias. So in something like linear regression, you have like the bias, which is your intercept, plus your weight, which is what you're multiplying by your value. So we have to have gradients for both of those. All right, and last but not least, extracting features. So the first 2 lines look just like transfer learning. We're just replacing the last layer of a model with the correct number of classes, loading the weights of the model that we've already trained, and then our very last line of code, we're just chopping off the very last fully connected layer. So basically we're saying the classifier is equal to everything in the classifier except the last one. All right. So a few other things to note. So I talked about fine-tuning. This is not an all-encompassing best way to fine-tune a neural network. It is one way that you should experiment with, along with a lot of other things, such as different architectures. I use the most basic transfer learning network there is. There's a lot of other VGG networks with tons more parameters. There's things like ResNet, which is state-of-the-art. You've probably heard of that. So it's worth looking at a lot of different architectures because they're all going to have different implications for your problem. Another thing, so we talked about how data is the most important thing when doing deep learning. That's still true when you're doing transfer learning. The more data you have, the better it's going to be. Sometimes you can't collect more data. So doing things like data augmentation, so taking all your images and rotating them a little bit, or blurring them, or cutting out different chunks of them to increase the size of your data set can be really helpful. Sometimes that makes a huge, huge difference, especially when you have small amounts of data. Other things, when you're tuning things like learning rates, what optimizer you're using, if you're going to decrease your learning rate, those things are all super, super important when looking at your neural network. And the last little tip is a lot of times the best way I found to build a neural network is to let it overfit a lot to your training data and then slowly bring it back with things like dropout or other types of regularization. So fine-tuning neural networks to your data set, super cool, super helpful, but definitely not the only way that you should look at tuning a neural network to provide a lot of value. All right, so that was everything I have. I have a link to my LinkedIn if you want to connect with me. If you don't care about me and just want to look at my code, that's the second link. It's totally fine, and I have no hard feelings. But on there, I think I have 8 notebooks that are at least somewhat correctly named. The code is not super, super clean because I wrote it really quickly, but hopefully after this presentation, you can understand what each part of it's doing. You can take it, you can run it, the data's up there too, and you can use it. So hopefully, those were like some of the easiest ways that you can take a neural network without having to write too much code and fine tune it and make it really applicable to whatever type of data you're working with. So are there any questions about anything? Yeah.
One question about the transfer learning. Do you have any conclusion in your experience of what is a fast ratio for the amount of data if you apply transfer learning? What's the ratio for the data between the original, like the ImageNet, and the image and your own image data set you are going to apply using transfer learning?
Yeah, that's a good question. I don't think there's a ratio. I think the more data you can get, always better. I have never gotten to a point where I thought, I have too much data. I better take some away so my network performs better. Like always, always, always more data is going to be useful. Yeah, always. I'm not aware of any exceptions to that, unless you have bad data, in which case you should probably get rid of that. But other than that, I think more data is always better. Any other questions? Yeah.
You know, transfer learning, how, like, when you go to like ship it, how does it impact the like size of the model? Like increase it like, tremendously or incrementally?
So I guess there's 2 ways you can approach it. If you're going to do transfer learning, you're going to load an architecture like we looked at. If you're not going to do transfer learning, you might not have a big architecture. So when you compare those 2 things, a smaller architecture is going to take a lot less time. But if you're going to use a big architecture, then having transfer learning is going to speed it up because you're going to get to your minimum a lot faster for your loss function. But in terms of overall compute time, the larger the network is and the architecture, generally the longer it's going to take. So something like the VGG16, which as it's named has 16 layers, versus the 11, is going to take a lot longer to train than the 11 is. So yeah. So that's also one of those things you kind of have to weigh. Where's the benefit of getting a lot bigger? And some of that you can learn by looking at data, like how deep in the features do you need to get? And some of it's just experimentation. You've probably heard neural networks considered black boxes, so we don't really understand that well what they're doing inside. So some of it's just experimentation and figuring out, is it worth it to take this extra compute time to add a little bit to my model or not? Yeah.
So what size were the cover images? Like what resolution were they?
Oh, I don't remember, but so all these models, transfer learning models, take pretty specific types of images, which I'm guessing is what you were alluding to.
Yeah.
So if you go look at my code, you'll see that I chop all the images into 224 by 224 images, and then normalize them with the correct mean and standard deviation that goes with that network. And I think pretty much all image classification models use the same standard normalization. So that's pretty easy to look up. But Yeah, I chopped them all to 224 by 224.
So how did you compress those then? I mean, what did you, because obviously it's going to affect the feature right on the image itself.
Yeah,
Changed essentially you reduced down the number of features that are available out of that model.
yeah,
So I mean, that's a consideration, right? When you're looking at
It
this
is.
type of thing. Like, how's compression going to affect?
yeah. So, yeah, like you alluded to, anytime you're going to chop images, you are going to lose some of your features, right? Because you're not looking at the whole image anymore. So, a few different ways to approach this. You can chop a certain part of your image. So if you know that whatever you're interested in is probably in the middle of the image, you can do a center crop and take the middle 224. Another way, which is what I did, you can just take a random crop of 224, which is going to take any random 224 by 224 block out of your image, which isn't ideal because ideally you want the part of your image that tells you the most information, but also it's a way to help regularize your network because you're not just getting one part of every image. You're going to see different parts of each image and learn different features. So there's the trade-offs, but if you experiment with it, using transfer learning and chopping your images is going to be way better than not chopping your images and not using transfer learning. Yeah.
Is there any value to chopping but scanning?
So like scanning the image to see which part has what you're interested in? Or
No, say you'll take the 224, shift by 1, and then shift down all the way across. So you're scanning the whole image.
got it. So
But
you've got
Like doing
so
you've got,
a convolution of it, right? You're not talking about that.
So you're talking about like creating like 6 images for the same book cover, which each takes a different chunk. Yeah, that's a form of data augmentation that can be useful. Yeah, I think that's a valid approach to try. It's definitely something that is a very popular form of data augmentation. Sometimes it helps, sometimes it doesn't, but it's definitely something that's worth trying, I think.
You didn't try it with compression at all. You didn't even try to keep the whole cover and just make it small. You just took a random part. It's interesting. Okay.
Yeah, I just randomly cropped it. Yeah.
Would you say compression, is that a valid form of data augmentation? Because you compress it like he was saying and kind of get more of the whole picture.
Ryan says no.
It's dimensionality reduction. You're losing features.
mean,
Well, I know you will, but if you have to get it to right.
Yeah, so I've played around with data augmentation a lot, and there doesn't seem like there's some things that like flipping an image over seems to do okay, and there's a lot of different things you can do. I'm very much of the opinion that it's worth experimenting with.
Sure. Okay.
I'm not sure it'll give you that much more information or different information, because the idea of data augmentation is you're going to give it a different input that is similar but different, right? So like as a human, if you look at image of a person and then you flip it over and you look at the same image of a person, it looks really different, but we can still tell it's a person. If a computer can do that, and then you give it a picture of someone doing a headstand, I guess they'll be able to tell that. So like, that's the goal of data augmentation, but I've seen some crazy things work. So I wouldn't be against that as an option. Maybe not the first option, but I mean, I don't think there's any bad ideas to try.
Cool.
It's kind of my approach to it.
So you're referring to actually taking that and adding it as well as another feature like the compressed version and like a crop.
Yeah, you could definitely do that. Yeah.
Any other questions? Yeah.
So your slides for feature extraction, you replace the original last layer of, so after the fully cleaned layer, there should be, originally should be the softmax function for classification problems or just a linear layer for regression problems, right? And you replace the last layer with the classical machine learning models where you use random forest. Have you used any other models, and according to your experience, what you relate is the best option for that machine learning model?
Yeah, so on this particular data, I only used random forest because I wasn't really that interested in comparing models. In practical applications, I am a big fan of Microsoft's Lite GBM. I found that in general, if you have a significant amount of data, it outperforms almost everything, almost always. Smaller amounts of data, it doesn't do super well with, but if you have a significant amount of data, I'm a big fan of that. Yeah. Yeah.
Is there any metric that says, what's the minimum amount of data that I need to get a certain amount of accuracy, or something to that effect? Because you say that the sample size is a big factor in accuracy. Just wondering, do you forecast and say, all right, I need this minimum sample size, and then after that, perhaps I'll try and change the hyperparameters and other aspects?
I mean, if anyone has an answer to this,
I would say just rule of thumb, and this is my interpretation of somebody else's rule of thumb, so this isn't doctrine. I don't think there's any doctrine on it. It depends on what type of model you're using. Neural nets, you're going to be wanting to look at tens of thousands, hundreds of thousands of data entries. Classical machine learning, you're closer to just thousands or hundreds if you're just trying to get a feel for what things are. Classical machine learning models don't necessarily work super well once you get to the hundreds of thousands, just because it's redundant. But neural networks work amazingly well once you have that much, because they do exactly what you want them to do in unstructured data. They find out what we can't see and then translate that into something usable. So that's my rule of thumb. And I've heard it from other people, but there is no there's no fast hard rule, just because the science is so new and it's constantly evolving.
Deep learning with small data is one of the biggest areas of research right now. Reiterate what she said. Just experiment, try it, and if it's nothing close to what you want, or if it's overfitting a ton, then you can assume you probably just don't have enough data. But yeah, yeah, that's it. Any other questions? All right.
Let's give him a hand. Thank you. I'll get this video up on YouTube and I'll post it on Slack. Thank you all for coming. Feel free to hang out as long as you want, or head home to the snow, grab more pizza. You can ask him more questions. Whatever.
Thanks.